Let's move on to the third example. In example 3, we have an investor that has to decide between the following two investment opportunities. Here's option 1. If he invests $300 at the end of every month for 3 years, he will get a return of $13,500 at the end of the third year. Option 2 is to invest $1,900 semi-annually for 3 years, and in return for that, they will get $13,900 at the end of the third year. We're asked to determine which option yields the highest rate of return on the investment. So we begin, as always, by looking at the time diagram. In option number 1, we've got 36 monthly payments of $300, and that's money out, and we will have money in of $13,500 at the end of the third year, so that obviously represents the future value or the final value after the third year of our deposits. And in option number 2, we have six semi-annual deposits of $1,900, and those deposits or payments will give us a return or an income of $13,900 at the end of year 3. So 6 semi-annual deposits or 6 semi-annual payments will amount to $13,900, whereas 36 monthly deposits will amount to $13,500. And the question is, which option is going to give us the highest rate of return on our investment? Well, in one case, I guess we could determine the monthly rate or the rate per month for the first option, option number 1. We could find the nominal rate compounded monthly and compare that to the nominal rate compounded semi-annually for option number 2. But that's not a very good idea, because if we did that, then we would be comparing apples to oranges, and we can't do that. We need to compare apples to apples. So the better thing to do would be to find the effective rate for both investments. So in this case, what we're going to do is we're going to determine the equivalent effective rate for both of the investments. And if we can know what the effective rate or the rate compounded annually for both of the investments, then we can compare the two effective rates and decide which one is the best option. If you were solving this algebraically and you didn't have access to the financial calculator, you would start off with the final value formula. $13,500 is equal to an annuity of $300 per month multiplied by the future value factor, 1 plus I to the power of 36 minus 1 divided by I, noting that I is the rate per month. Now you'll divide both sides by $300 and you end up with a factor of 45 is equal to 1 plus I to the 36 minus 1 divided by I. And now you've got 45 as your target, and you will interpolate. You're going to try different values for interest rate until you narrow it down to a 0.5% interval. And in fact, you will narrow it down to somewhere between 1% per month and 1.5% per month. You always have to make sure that one of your rates has a factor above 45, and one will have a value of a factor below 35. You'll set up your table and interpolate between those two using ratios, a ratio of differences, and you will have an approximate value of 14.8% compounded monthly, and 14.8% compounded monthly will translate to an effective rate of 15.87%. Effective means compounded annually. Well, if you have the BA2 Plus calculator, let's see what happens with the BA2 Plus. Again, remember that with the BA2 Plus calculator, you're going to clear your registers. So remember to clear the registers first. Then you're going to enter in the final value is $13,500. So $13,500 represents the final value. So you're going to key that into your calculator. You're going to enter in 300, but no, wait, you're not going to enter in 300. You're going to enter in negative 300, and negative 300 is the payment. Remember that payments are always the opposite sign of the either the present value or the future value. So the money in is $13,500. The money out is $300 per month. Now we're going to key in the rest of the information. We've got 36 payments, so N is the number of payments, so we're going to key in 36, and then we're going to go second function IY, second function I/Y to key in the information about the interest. The payments per year, P/Y, is equal to 12. There's 12 payments per year, and compounding periods per year, we might as well enter in 1 and go right to the effective rate. So 1 will be the effective rate. So annual rate and monthly payments. So now we're going to enter in second quit to get out of the secondary functions, and now we're going to compute the CPT, compute the I/Y, and your calculator will tell you that the effective rate is 15.88596 and so on percent per year, and we'll round that off to an effective rate of 15.89% effective. Now we have to compare that to option number 2. Looking at option 2, the time diagram, and solving this algebraically, we would use the future value formula again. 13.9 is equal to $1,900 multiplied by the final value factor 1 plus I to the power of 6, because there's 6 deposits, minus 1 divided by the interest rate. And remember that the interest rate is per 6 months, not per month now, and it's not effective either. So it's a per 6-month rate. So we divide by $1,900 and we end up with 7.3157 and so on. I'm going to round that off to 7.32, and that's equal to the annuity factor 1 plus I to the power of 6 minus 1 divided by I per 6 months. And interpolating, you will end up interpolating it and determining that it is between 7.5% and 8% compounded, or 7.5% and 8% per 6 months. Or when you interpolate using the ratios, equivalent ratios, you will end up with a nominal rate compounded monthly of approximately 15.8%. So it would end up being somewhere between somewhere close to 15.8% compounded monthly. And of course, this rate compounded monthly would need to be converted to an equivalent rate compounded annually to get our effective rate. So this would translate to an equivalent effective rate of 16.4% approximately effective. Now, we can all probably do a better job of working this out on our calculators using the built-in functions. So let's list what those entries would be. So on your financial calculator, you would be keying in the following values. Of course, you would have to clear your calculator first using second clear TVM. Enter in $13,900 as the final value. Negative $1,900 is the PMT, or the payment. 6 is equal to the N, and go second function IY to go into the secondary values for the interest rate. PY, P/Y, or payments per year are 2, because there's 2 semi-annual payments per year. Press the enter key after you've changed it to 2. Toggle down to, using the down arrow button, to CY, compounding periods per year. Make that equal to 1. Press the enter key and then go second quit. Second quit, and now compute. You're ready to compute the IY, and your calculator will return to you the interest rate per year, or the effective annual rate. And this works out to 16.40465% effective, or let's rounding that off to 2 decimal places, it would be 16.40% effective, which is pretty much what we got algebraically or manually. And so we can now put all of our information together and go back to our time diagram. Option number 1, which gives us $13,500 in return for $300 per month deposits. This gave us a return rate of 15.89% effective. So 15.89% effective was the annual return on our investment in this first case. And in the second case, where we got $13,900 income in exchange for $1,900 per 6 month semi-annual deposits, this gave us a return of 16.40% effective. So we're comparing two rates that are equivalent. They are compounded annually, and so it's obvious here that the one that we would choose would be the 16.40%, because it gives us a higher return for our investment. We're going to get a greater return on our investment dollars.